Greetings to my dear students. So in this video, we are going to learn about Cauchy's theorem and Cauchy's integral formula and problems regarding Cauchy's theorem and integral formula. Okay. So first, let us see the statement of Cauchy's theorem and Cauchy's integral formula. Okay. So Cauchy's theorem statement is let f be a function which is analytic at all points inside and on a simple closed curve C, then integral of f of z over the simple closed curve C is 0. The integral value of f of z over the simple closed curve C is 0. So what's the meaning behind it? Okay, so first let us consider a simple closed curve C. Okay, so this is a simple closed curve C. Okay, wait a minute. Yeah, so this is our simple closed curve C. And let f be a function which is analytic at all points inside and on a simple closed curve C. So we have a function f of z. So we have a function f of z which is analytic inside the curve and on, which means it's analytic inside and in the boundary. In everywhere on the simple closed curve, it's everywhere the function f of z is analytic. So what is meant by analytic? A function f is said to be analytic at a point. It's a global property. Analytic at a point. First, we will check the analytic at each point. If it is analytic at every point, then we will say that the function is analytic at everywhere. Okay. So first, we will check the analytic at a point. Okay, so say a function f is said to be analytic at a point. For each point, okay, for each point, listen carefully, for each point we have a neighborhood. Okay, for each point we have a neighborhood. Among those neighborhood, if the function f is differentiable at every point of at least one neighborhood. Okay, uh, okay. Okay, so here, okay, so consider this as a point. Okay, a point A is said to be analytic. Okay, wait a minute. F of Z is said to be analytic at a point A or at point A if F is differentiable at every point of some neighborhood of A. Okay, so this is the definition of function f is said to be, a function is said to be analytic at a point. Okay, so for each point we have infinite number of neighborhoods around. Okay, we have infinite number of neighborhoods. Sorry. Okay, so first let me draw a real axis. Okay, so consider this as a okay, consider this as a real line. Okay, so here we have a point A. Okay, I have a point A. So for this point A, I can find so many neighborhoods with the center at this point A. Okay, I can have this as a neighborhood. I can choose this as a neighborhood for A, and I can choose this as a neighborhood for A. Okay, so we have infinite number of neighborhoods. Okay, in this neighborhood, if suppose the function, okay, suppose the function f is differentiable at every point. Okay, the function f is differentiable at every point in this neighborhood. Okay, every point in this neighborhood, every point in this neighborhood, then we can say that the function f is analytic at the point A. Okay, so this is the definition of a function f is said to be analytic at A. If the function f is analytic at each point, so we have some domain omega in this. Okay, so we have I don't know why it is. Wait, okay, so in we have some region omega. In that region, for each point is analytic. Okay, for each point has the properties analytic, then we can say that the function f is analytic at in the whole region. Okay, first we will check the analytic at a point. Okay, we check analytic at a point in where A belongs to, A has some domain, isn't it? So from A belongs to some omega, so f is analytic at all points in the region omega, then we say that the function is analytic. Okay, if it is not, yes, at some situation it is analytic only at some points. In some other points it may not be analytic. So in that case, we couldn't say that the function is analytic. A function is analytic means it's analytic at each point. Okay, each point in the domain. Okay, so I hope this definition is clear. So, wait a minute. Okay, so this function, so we have given that the given function is analytic, instant, and a simple closed curve C. Then the integral value, you don't need to check the value. You don't need to evaluate the integral value. Automatically, you can say that this integral value over this simple closed curve is 0. Okay. So next definition, Cauchy's integral formula. F of Z be a function which is analytic inside and on a simple closed curve C. Let Z not be any point in the interior of C. Z not be any point in the interior of C. Then f of Z naught is equal to 1 by 2 pi I integral over C f of Z divided by Z minus Z naught dz. Okay. So let us see the meanings behind this one. Okay. So as in the Cauchy's theorem, we have a simple closed curve C. We have a simple closed curve C, and f of Z is analytic. Okay. So f of Z is analytic in this simple closed curve. Sorry. So we have given that the f of Z is, we have a simple closed curve C, and the function f is analytic in and on a simple closed curve Z. And is that not be any point in the interior of C? Okay, is that not be any point in the interior of C? Okay. Okay, so we have a simple closed curve, and is that not be any point in the interior of C? Okay, so this is C, this is C, and we have the point is it not inside the simple closed curve Z. Okay, now look at this function. Okay, look at this function f of Z by Z minus Z naught. When you substitute the value Z naught in this place, what will happen? What will happen? Clearly, this tends to infinity, which means analytic fails at this point. The analytic fails at this point, okay? And moreover, this point lies inside the simple closed curve. So which means the function is analytic at all points inside the simple closed curve C, except at the point Z naught. Okay, except at the point Z naught, which means this point is a singular point. We can say in other words a singular point. Okay, we will see later. Okay, but for now, at this point Z naught, the analytic fails. So if it is, if such a point exists, then how we find the integral value of f of z over the simple closed curve Z? This is what Cauchy's integral formula. If the function fails to be analytic at a point z naught, then the integral value of this, the integral value of this over the simple closed curve except at the point z naught is nothing but 2 pi I into this will goes this side, 2 pi goes to this side, 2 pi I into f of z naught. Okay, so if a function is analytic except at a single except at a point, then the integral value over the simple closed curve is nothing but 2 pi I into f of z naught. So we have a function f of z, it's given function. In that function, you have to substitute the value z naught and multiplied by 2 pi I will give the integral value of this function. Okay, so I hope this definition is clear. Cauchy's theorem and Cauchy's integral formula is clear. So now we will see examples one by one. Okay. So first example, solve problem 1. Evaluate integral over c dz by z minus 3, where c is the circle mod z minus 2 is equal to 5. So here we have the simple closed curve as a circle. So circle mod z minus 2 is equal to 5. Okay. This means what? Okay. This means what? It's a circle. Okay, this is general form of a circle, isn't it? What is general form of a circle? Modulus of z minus a is equal to r. This is the general form of the circle, which means it's a circle with the center a and radius r. Okay, so it is a circle with the center. It's a circle with the center a and radius r. So here we have the center as 2 and the radius as 5. Okay, so we have the center as 2 and radius as 5. So when we draw this one, okay, so it's a straight line. Okay. Um, okay. So this is point 2. Okay. This is the point 2. So it's a center point 2. Radius is 5. So this is 3, 4, 5, 6, 7. So we have the radius, distance is 1, radius 1, radius 2, radius 3, radius 4, radius 5. And this negative side we have, the left side we have, this is 1, 0, minus 1, minus 2, and this is minus 3. So the circle happens to be, this is not a circle, it's an ellipse. Okay, consider this is a circle. Okay, so this is the circle with the centers 2 and radius 5. Okay. So just I'm simply drawing one circle with the, this is a circle with the center 2 and radius 5. Okay, circle with the center 2, circle. Okay, this is center point. So center 2 and radius is 5. Okay. Okay, so here what happens? Okay, so what are the things we need to check here? First, look at the point. Look at this one. Okay. At which point this analytic fails? Of course, the point is 3. If we substitute 3 in the place of z, this analytic for this function fails. For which function? 1 by z minus 3. For this function, the analytic is fails. Okay. So the f of the function is analytic at all points inside the circle except at the point 3. Next we have to check that whether this point lies inside the circle or outside the circle. That should be a very important thing. We have to check in where the analytic fails, that point, whether it lies inside the circle or outside the circle. Okay. So here the point 3. Okay. The point 3 is obviously lies inside the circle, isn't it? Because it's a circle with the center 2. Okay, circle is in. So here 3 lies here and this is 4. And okay, this is 4, this is 5, and this is 6, this is 7. So radius 5 means we have up to this much. Okay, up to this much we have. So clearly the point 3 lies inside this circle. The point 3 lies inside this circle. Okay. So the point 3 lies inside the circle, which means we can hear which Cauchy's theorem or Cauchy's integral formula, which one we have to use here? Of course, the Cauchy's integral formula, because the function the analytic fails at the point 3 and the point 3 lies inside the circle. This is what Cauchy's integral formula means. The point lies in the interior of C. So here the point 3 lies inside the circle. So by Cauchy's integral formula, what we get? Integral over C, this one, integral over C f of z divided by z minus z naught dz is equal to 2 pi I into f of z naught. Okay. So here what is the value of f of z? What is the value of f of z? What is the value? Here in the numerator part, we don't have nothing, which means we have we can take f of z as 1 because 1 is here, isn't it? So I can take f of z as 1. The point 3 lies inside the circle C. So therefore, by Cauchy's integral formula, Cauchy's f of the point 3 is equal to 1 by 2 pi I integral over C f of z divided by z minus z naught dz. Suppose here we have by Cauchy's integral formula f of 3 is equal to, here z naught is 3. So therefore f of 3 is equal to 1 by 2 pi I integral over C 1 by z minus 3 dz. Now we need the value of with this one, isn't it? We need the value of this one. Which one? We need the value of this one. Suppose, so one integral of 1 minute. Okay. So the integral of this is equal to 2 pi I into f of 3. But what is f of z? F of z is equal to 1. It's a constant mapping. It's a constant function. So for all points, the mapping goes to 1. Mapping goes to 1. So for f of 3, same f of 3 is equal to 1 because for all points z in the domain, the image is 1. So for the point 3 is also the image is 1. So the f of 3 is nothing but 1. So therefore 2 pi I into 1 is equal to 2 pi I. So now we evaluate the integral over C dz by z minus 3. So if they are asked to find the integral value of you should remember this, that first you need to write the f of z. Okay, you need to write f of z. The denominator part should contain only this one. Which one? In the denominator part, it must be of the form z minus z naught and no other. Okay, it should be some z minus z naught. The remaining things we can take it as f of z. Okay, the new denominator part should contain z minus z naught form only, and the remaining functions, the remaining things we can take it as f of z. Okay, then we have to check whether the point where the analytic fails lies inside the circle or inside the curve or outside the curve. If it is lies inside the curve, then you can use Cauchy's integral formula. If it is lies outside the circle, outside the curve means what happened? If the point, suppose, okay, so this is a curve, okay, and is it not is a point, okay, is a point lies outside the circle means what means sorry, it means what? The function is analytic at all the points inside and on the simple closed curve C. Because since the analytic fails at the point where is that not only, but that is that not lies outside the circle means The function f is analytic at all points inside and on the simple closed curve C. So in that case, if the point lies where the analytic fails, and that point lies outside the circle means, outside the curve means, we can use Cauchy's theorem in that place. Okay, you should not use Cauchy's integral formula, because Cauchy's, if you have to use Cauchy's integral formula means the point in where the analytic fails must lies inside the circle. If it is lies outside the circle, it implicitly shows that at all the points inside the circle and on the boundary points, the function is analytic. So therefore, you can use Cauchy's theorem, not Cauchy's integral formula. Okay. So I hope this is clear. In the next video, we will see the upcoming, the remaining problems. Okay. Yeah. Thank you, dear students.